Good day, we'll be discussing now Hamiltonian paths and circuits. So these graphs were first discovered by Sir William Rowan Hamilton. That's why they are called Hamiltonian paths and circuits. He invented this one using the I-quotient game idea. It is also known as Hamilton's puzzle. Now this game involves finding a Hamiltonian cycle or circuit in the edge graph of the dodecahedron. So it looks like this. Now, what is a Hamiltonian path? A Hamiltonian path is a path that visits each vertex of the graph exactly once. Take note, our main concern here is or are the vertices. Unlike in Euler graph, our main concern there are the edges. So in Hamiltonian path, our main concern is or are the vertices. So in Hamiltonian path, all edges may or may not be covered, or the edges may not be covered at all. So it's not a requirement that you should cover all the edges. Now in this case, we have these two graphs. For this one, we can have a Hamiltonian path if we start from A to B to C to D to E. Now if you notice, I have visited all these vertices A, B, C, D, and E, and I did not cover all these edges. Okay, so that is Hamiltonian path. Our main focus is on the vertices. Now on this graph, we can have A to B to C to F. If you go to E, then of course, I think it will be difficult for you to cover all the vertices, because if you go to E, you have two choices. You go to D and you go to G, but of course you cannot go back to E because we must only visit each edges once. Now if you go to each edge once, if you go back to H, then of course you cannot cover D and G. So in this case, we can have A to B to C to F to H to E to G and last to D. You can have that one. Or if you want, you have another one, A to B to C to F to H to E to D and to G. Okay, so just take note that we must visit each vertex once and the edges may not be visited or covered at all. Note or notes, in Euler paths, the concern is on visiting each edges exactly once. Further, vertices may repeat. However, in Hamiltonian path, the concern is on visiting each vertex exactly once. Further, edges must not repeat and may not be passed. So let's have this. Give a Hamiltonian path if it exists. Okay, say one of a Hamiltonian path of the first graph, we can have A to B to C to D to E. Okay, you can have other Hamiltonian path as well. You may start at B, you may start at C, you may start at D, or you may start at E, as long as you can visit all the vertices once. Now for number 2, we can have A, B, D, C, or you can have A, B, C, D. Okay, or you can start with C, D, B, A. Okay, again, the same with Euler path and Euler circuit. The answers for this one may not be unique. So you can have other answers as well. For graph number 3, can you find a Hamiltonian path in this one? So let's try. If we have A, B, G. If you go down to E, then you have two choices. If you go to C, then of course you cannot go back to F. But if you go to F, you cannot go back to C. So in this particular problem, if you may try other things, you cannot visit all of these vertices. So it has no Hamiltonian path. For this one, for the last graph, we have A to B to D to C to E, F, and to G. So we have this as one of the Hamiltonian path. Okay, so we have this. You may pause the video to check whether our path here is correct. We have another answer and this one. So you may practice this. You may pause this video. So basically for the first part, it's very easy. So you can have A to E to B to D to C. Okay, that is one of the Hamiltonian path. For the second one, of course, we should start here. E to D to B to A and to C. And of course, the last one, if, if you start at any vertices A, E, C, D, then of course, it's very difficult to get the other vertices. For example, if we go to C, we go to B. And then if you go to A, then you cannot come back. If you go to E, you cannot come back to the other vertices. If you go to D, the same thing. So the last graph has no Hamiltonian path. Now let's go to Hamiltonian circuit. A Hamiltonian circuit is a path. So it's still a path that uses each vertex of a graph exactly once and returns to the starting point. So meaning every Hamiltonian circuit is a Hamiltonian path. So it's just closed because it starts and ends with the same starting point or vertex. But not every Hamiltonian path is a Hamiltonian circuit. Now take note that a graph that contains a Hamiltonian circuit is called Hamiltonian. So examples of Hamiltonian circuits. So give an example of this. So I'll just give one. So we have A to B to D to G, E, H, F, C, and back to our starting point A. So this is Hamiltonian because it has a Hamiltonian circuit. On this part, we have A to B to C to E to D back to A. So it's a Hamiltonian circuit. Again, since it's Hamiltonian, it does not require us to cover all the edges, only the vertices. So, and also, the answers for this one are not unique. You may have your own answer as you have visited all the vertices. So using the equation game, we have these other answers for the equation game. If you notice, the edges are not visited. Some of the edges are not visited at all. Note, in Euler circuits, the concern is on visiting each edge exactly once. Further, vertices may repeat. And in Hamiltonian circuits, again, the concern is on visiting each vertex exactly once, and the edges may not be passed. Some of the edges may not be passed. Now let's go back to this graphs. Give the Hamiltonian circuit. Okay, take note. We have this answer for the Hamiltonian path when we discussed the Hamiltonian path a while ago. Now, so we have A, B, C, D, E. Take note, in order for this to become a circuit, we can just add A because we'll just go back to its starting point A. Similarly, for the second Hamiltonian path, we can just add again the starting point, which is B. Because take note, every Hamiltonian circuit is a Hamiltonian path. So this is a Hamiltonian circuit, and we can also treat this as a Hamiltonian path, a closed path. Next, for this one, this is our Hamiltonian path, or these are our Hamiltonian paths, but we cannot find any Hamiltonian circuit. Okay, say for example, if we start with A, this one ah, A, B, C, D. Okay, so we cannot go back to B. A, B, D, C, we cannot go back to B. If we start with B, D, or C, of course, because of this one, we cannot go back to either of the other vertices. And take note that not every Hamiltonian path is Hamiltonian circuit. That is why we have this. We have a Hamiltonian path, but we cannot find a Hamiltonian circuit. Next, of course, we have no Hamiltonian path, and at the same time, we have no Hamiltonian circuit. You may pause the video if you want to try, if you want to find a Hamiltonian circuit in this particular graph. And last graph, we have this. These are some of our answers for Hamiltonian path. So let's try A to B to D, C, E, F, G. In order for this to become a circuit, we'll go back to A. Let's start with this one, E. So E, C, D, B, A, G, F, and then go back to E is another circuit, Hamiltonian circuit. Again, every Hamiltonian circuit is a Hamiltonian path. So your turn. Give a Hamiltonian circuit for this one. For number one, we can have A, E, B, D, C. Go back to A. For the second graph, there's no Hamiltonian circuit, as well as with the third graph. Again, if you want to make some changes with this answer, if you want to answer this one, if you think that these two has Hamiltonian circuit, then you may pause the video and try them on your paper. Now let's have this Dirac's theorem. Consider a connected graph with at least 3 vertices. So n is greater than or equal to 3, the number of vertices, and no multiple edges. Let n be the number of vertices in the graph. If every vertex has a degree of at least n over 2, then the graph must be Hamiltonian. So in short, we can only use the Dirac's theorem if it satisfies the given. First, it must be that the number of vertices is greater than 3, and the degree of every vertex is at least n over 2. And if these two are satisfied, then we can conclude that the graph must be Hamiltonian, meaning there is a Hamiltonian circuit. But if this assumption is not satisfied, that every vertex has a degree of at least n over 2, if this is not satisfied, then we cannot use the Dirac theorem. We cannot conclude that the graph has no Hamiltonian circuit. I repeat, if the assumption is not true or is not satisfied, then we cannot use this Dirac's theorem. We cannot conclude that the graph must be Hamiltonian. We can only use this theorem if it satisfies these two requirements. Say, for example, is the graph Hamiltonian? If it is, give a Hamiltonian circuit. Okay, so let's try first the Dirac's theorem. Now, the number of vertices is 8. So 1, 2, 3, 4, 5, 6, 7, 8. So n over 2 is 4. So n is 8, that is greater than 3, so satisfied. And each vertex has at least 4 degree, or the degree is 4. Okay, the degree of at least n over 2. So with this, we can say that by the Dirac's theorem, the graph must be Hamiltonian. And again, if it is Hamiltonian, then we can find a Hamiltonian circuit. So these two are examples of Hamiltonian circuits. So let's try number 1. A to B to E to H to D to C to G to F and then go back to A. Okay, you may try the other one. Now next is the graph Hamiltonian. Again, let's try Dirac's theorem. N is 7, so it's greater than or equal to 3, so satisfied. And then using this one, n over 2 is 3.5. So looking at the degrees, 4 and 5 are both greater than 3.5. So we can now use the Dirac's theorem. Thus, the graph must be Hamiltonian. So one of the circuits or Hamiltonian circuits is this A to B to C to D, G, F, E, A. And again, you may pause the video and try the other Hamiltonian circuit. Now, this is what I told you, that the inverse and the converse of this theorem is false. Or we cannot directly say that if this is false, then of course, there is no Hamiltonian circuit. Okay? So for example, determine whether the graph below is Hamiltonian or not. If it is, then give or find a Hamiltonian circuit. If it is not, explain why. So if you want to use the Dirac's theorem, so the Dirac's theorem, it says that the n, the number of vertices, must be greater than or equal to 3. It should be greater than or equal to 3. Now, what is the number of vertices? 1, 2, 3, 4, 5, 6, 7. So it's 7, so satisfied. How about n over 2? We have 7 over 2 is 3.5. Okay, 3.5. But take note, vertex A has degree 2. Right? It's degree 2. So since this one is not satisfied, then we cannot use the Dirac's theorem. Okay, we cannot use the Dirac's theorem in answering this question. Okay. Okay. So, but it does not necessarily follow that the graph is not Hamiltonian. Okay, so that is why if the premise or the condition is not satisfied, then we cannot negate the conclusion that there is no Hamiltonian circuit. Okay, so in this particular example, okay, there is using the Dirac's theorem, or we cannot use the Dirac's theorem, I mean. Okay, but we can find a path or a circuit. This is a circuit because it starts and ends with the same vertex, and at the same time, it's also an Hamiltonian path. So let's try A, B, C, D, E, F, G, A. So that is our Hamiltonian circuit. So the point here is, if the premise of the Dirac's theorem is false, then we must not use the Dirac's theorem in determining whether the graph is Hamiltonian or not. Okay. Now let's have this application. The graph below shows the available flights of a popular airline. An edge between two vertices indicates that there is a direct flight between two cities. Apply Dirac's theorem to verify that the graph is Hamiltonian. Then find a Hamiltonian circuit. So since we are asked to use the Dirac's theorem, of course, we'll start with the degrees. Okay, so the number of vertices, we have 10. And the degree of the vertices must have at least n over 2, which is 5. The degree is n over 2, or at least 5. So If you notice, we have 5, 6, 7, and 9. So it satisfies the premise of the Dirac's theorem. Thus, the graph is Hamiltonian. Okay, then the second question is find a Hamiltonian circuit. So one of the Hamiltonian circuit is this. So let's try. From Manila, so start from here. Manila to Tokyo, to Seoul, to Taipei, up, and then Hong Kong, Macau, Bangkok, Ho Chi Minh, Kuala Lumpur, Singapore, and go back to Manila. And you may pause the video, of course, if you want to find another Hamiltonian circuit.